For centuries, it's been one of the biggest riddles in science. I mean, we see it, we feel its warmth, it powers our entire world, but what is light, really? So let's dive in and see if we can uncover its true identity.
And this was the central question, the one that divided the greatest minds in physics for hundreds of years. Was light a stream of tiny, microscopic bullets, or was it more like a ripple moving through space?
So on one side, you've got the particle theory, light as a collection of tiny, individual packets of stuff, and on the other, you have the wave theory, light as a continuous, flowing disturbance. These were our two main suspects, and believe me, each one had a very powerful champion in its corner.
Our investigation starts with an absolute giant of science, Sir Isaac Newton. And he was firmly in the particle camp, developing what came to be known as the corpuscular theory of light. You know, Newton's idea was beautifully simple. He figured light was made of these tiny, massless corpuscles that just shot out in perfectly straight lines. And this explained reflection perfectly. It was just like a tiny ball bouncing off a mirror. It even seemed to explain refraction, the way light bends when it hits water. His theory was that these little corpuscles actually sped up when they entered something denser.
But even for a genius like Isaac Newton, the model wasn't quite perfect. There were certain things that just didn't really fit this simple particle picture. And these little inconsistencies, well, they started to cast some serious doubt on the whole idea.
Okay, think about the surface of a pond for a second. You can see your own reflection in it, right? But you can also see the fish swimming around at the bottom. This is called partial reflection, and it was a huge problem for Newton. Why would some of these identical little corpuscles bounce off the water while others just sail right on through? Newton didn't have a good answer. He was basically forced to suggest it was just random chance. And that, well, that's a pretty big weakness for such an elegant theory.
So, as these doubts about the particle model started to grow, an old rival theory began to gain some serious ground. The idea that light wasn't a particle at all, but was actually a wave, was about to have its moment in the spotlight.
Now, the key to the wave theory is this unique property called interference. See, when two waves overlap, they can either add up to create a bigger, more powerful wave, or they can completely cancel each other out, leaving nothing. And this is a special trick that only waves can do. Particles just don't act like that.
The big breakthrough came in 1801 with Thomas Young's now famous double-slit experiment. He shone a beam of light through two tiny little slits. Now, if light were just particles, he would have seen two simple bright lines on the other side. But that's not what he saw. Instead, he got this weird pattern of multiple bright and dark bands. This was the smoking gun. It was an interference pattern that could only be created by waves.
After that, the evidence just became overwhelming. The wave theory perfectly explained interference. It also correctly predicted that light actually slows down in water, the exact opposite of what Newton's theory said. And by the time James Clerk Maxwell's equations described light as an electromagnetic wave, the case seemed totally closed. Light was a wave. End of story. Or so they thought.
For almost 100 years, the wave theory ruled physics. But then, right at the turn of the 20th century, a brand new mystery popped up, a phenomenon that was about to throw everything, and I mean everything, into question all over again. It was called the photoelectric effect. Here's the deal. When you shine light on a piece of metal, it can knock electrons loose. But here's the totally bizarre part. It only worked if the light was the right color, or what scientists call frequency. A dim violet light could knock electrons out instantly, but a super-duper bright red light did absolutely nothing. And making the light brighter only changed how many electrons got knocked out, not if they got knocked out in the first place.
This was a complete and utter disaster for the wave theory. According to all the rules of wave physics, a bright enough wave, no matter what color it was, should have eventually delivered enough energy to knock an electron loose. But the experiment showed this was just plain wrong. The theory had failed, big time.
And then along comes a young Albert Einstein with a totally radical solution. He asked, what if light isn't a continuous wave after all? What if it's actually made of individual little packets of energy? He called them photons. And this explained everything. A single violet photon had enough of a punch to knock out an electron all at once. A red one just didn't. All of a sudden, the particle was back in the game.
So, after centuries of debate, what was the final answer? Was Newton right? Was Young right? Well, the shocking conclusion was that they were both right. Light, it turns out, has a dual identity. And this is the bizarre, mind-bending heart of quantum mechanics, wave-particle duality.
Light travels through space like a wave, spreading out and creating those interference patterns. But the very moment it hits something and interacts with matter, bam, it acts like a particle, a single photon delivering a tiny, concentrated punch of energy. One physicist at the time joked about it with this perfect quote, which really just captures the utterly strange nature of this new reality. I mean, it sounds completely impossible, but it's what every single experiment has confirmed to be true.
And just when you think it can't get any weirder, the rabbit hole goes deeper. A few years later, a physicist named Louis de Broglie proposed that this isn't just about light. Everything, electrons, atoms, even you and me, has both particle and wave properties. This crazy discovery became one of the fundamental principles of our entire universe.
Okay, so why does this bizarre riddle even matter? Well, because solving it didn't just rewrite a bunch of physics textbooks. It unlocked a technological revolution that literally built the modern world we live in today. You see, understanding the photon led directly to the development of quantum mechanics. And that knowledge was absolutely essential for inventing the transistor back in 1947. That's the tiny little switch that's at the heart of every single computer, smartphone, and modern electronic device. Lasers, LEDs, solar panels, all of it exists because we finally solved the riddle of what light is. So the next time you use your phone or flip on a light switch, just remember the centuries-long scientific detective story it represents. And it really makes you wonder, doesn't it? What seemingly impossible questions are scientists wrestling with right now that are going to completely reshape our future?